Welcome to The Explainer. We're all using these incredibly powerful AI tools, right? But have you ever stopped to wonder how they're actually made? Well, today we're going beyond that black box to break down the first crucial steps in creating a large language model, from just raw data to a working brain.
Albert Einstein had this great way of putting it. He said the whole point of science isn't just to know that something works, but to understand why it works, right? From the most basic principles. And that's exactly the journey we're on today with AI, trying to turn what feels like a magic trick into a real, understandable science.
All right, let's dive right into our first section, the AI black box, because this really gets to the heart of the paradox of its power. So here's the crazy situation we find ourselves in. We have these tools that are changing the world, but our actual scientific grasp of how they work on the inside is, as one paper puts it, disproportionately nascent. Basically, they work incredibly well, but the deep why is still a massive mystery. It's kind of like we built a jumbo jet that flies perfectly, but we're still a little fuzzy on the laws of thermodynamics.
This brings us to the big question, doesn't it? How do we even begin to map this incredible, complex new territory? How do we go from just being great engineers to becoming real scientists about it?
So how do we find our way? Well, the answer starts with a clear roadmap. And that brings us to Section 2, a life cycle for LLMs. This is our roadmap for understanding. To get a handle on all this, researchers are proposing this unified six-stage life cycle that organizes the whole process from start to finish. Think of it as a way to bring some order to the chaos, breaking down this massive undertaking into distinct, understandable chunks. It gives us a map we can actually follow. Now, we're not going to tackle all six stages today. Instead, we're going to focus on the absolute bedrock of creating an LLM, the first three stages. Seriously, think of it like building a skyscraper. You have to get the foundation, the architectural blueprint, and the core construction absolutely perfect before you can even think about anything else. So let's start at the very beginning. Section 3, Stage 1, laying the data foundation. And believe me, this is way more than just scraping a bunch of text off the internet. It's a critical scientific process in itself. So here's the one thing you absolutely have to understand. Data is everything. I'm not exaggerating when I say that the data a model is trained on, it sets the absolute ceiling for what it can ever hope to achieve. Its knowledge, its ability to reason, even its flaws and biases, it's all born right here in the data. But this total reliance on data brings up a huge challenge: memorization. This is what happens when the model stops being a student that learns concepts and starts acting more like a photocopier, just spitting out things it's seen before, word for word. And that leads us to this fundamental trade-off. On one side, you have memorization, just recalling answers. That's not just lazy, it's brittle, and it can even lead to serious privacy risks. On the other side, you have generalization. That's the real prize. It's the ability to learn a pattern and then apply it to solve a totally new problem it's never seen before. It's the difference between cramming for a test and actually understanding the subject. And the stakes here are really high. Get this. One pretty shocking study found what they called a cliff-like decline in GPT-4's performance on coding problems that came out after its training data cutoff. This was a massive red flag. It suggested that a lot of its incredible success wasn't just pure reasoning, but was heavily propped up by having memorized solutions it had already seen in its data. Okay, so we've established that getting the data right is job one. Now, what do you build on that foundation? That brings us to Section 4, Stage 2, designing the model blueprint. We've got our raw materials, now we need the architectural plans. This is the stage where you pick the core engine of the LLM, the architecture. And the most famous one by far is the transformer, is literally the blueprint that determines the model's fundamental abilities and its limits. It defines how information flows, what kinds of patterns it can even recognize, basically what it's capable of learning in the first place. But just like with anything in engineering, there is no free lunch. Every single architectural choice you make comes with a trade-off, and the biggest one is this constant tug-of-war between a model's raw power and its efficiency. Let's break that down. On one hand, you've got your standard transformer models. They are incredibly powerful, no doubt, but their computational cost just explodes as the text you feed them gets longer. For example, if you double the input length, the compute needed can actually quadruple. On the other hand, you have newer, more efficient designs, linear models, where the costs scale up much more gently. The risk? Well, they might not have the same raw, expressive power as the heavyweights. It's a classic trade-off. So we have our data foundation and we have our model blueprint. Now it's time for Section 5, Stage 3. This is where it all comes together, the great training process. Now, training isn't just one big event. It's really a two-phase process. First up is pre-training. Think of this as the brute force phase, where the model essentially reads a giant chunk of the internet, trillions of words, to learn the basics of language, facts, and even a bit of logic. Then comes supervised fine-tuning, which is a much more delicate process where we use high-quality examples to teach the model how to be useful and follow human instructions. And this is where things get really wild. The core task during that massive pre-training phase is almost laughably simple. Just predict the next word in a sentence. That's it. But when you do that billions and billions of times, something truly incredible starts to happen. You get what researchers call emergent capabilities. These are complex skills like doing math or writing code or summarizing a long document that nobody ever explicitly programmed into the model. They weren't in the instruction manual. They just appear out of nowhere once the model and the data get big enough. It's one of the deepest mysteries in the field.
So let's zoom out for our final section and look at the big picture. All of this work, all these stages, are part of a much larger, more important shift, moving from just engineering these things to actually creating a science around them.
So the real takeaway here is this. The era of building LLMs being some kind of mysterious art based on guesswork and gut feelings is starting to end. By creating structured frameworks like this life cycle and really digging into the internal mechanics, we're slowly but surely building a true, principled science of AI. And that is what's going to let us tackle the really, really big questions. Which leaves us with one final, massive question to chew on. As we methodically crack open this black box and really start to understand how these things work, are we just getting better at engineering complicated machines? Or are we maybe, just maybe, starting to uncover the fundamental principles of intelligence itself?